For our glider, we kept to a relatively simple but very effective design. Our initial inspiration came from the image on the top, but we modified certain aspects to best maximize the efficiency of our glider. The sketch on the bottom shows our design for the glider. For the fuselage, we have a carbon rod, and at the tip we attached some blue tack that allowed us to easily adjust the center of gravity by either taking away some or adding more. Our wings consisted of 3D printed ribs shaped as the NACA 4412 airfoil, thin carbon rods as the spars, and baking paper as the skin of the wing. The tailplane was made of balsa wood, and the vertical stabilizer was attached to the horizontal stabilizer with superglue. Both the wings and tailplane were attached to the fuselage using rubber bands, which allowed the location of them both to be easily adjusted as needed during testing. The dimensions we initially decided on are shown in the diagram. However, the final dimensions of our glider were slightly altered after testing to achieve the best glide possible.
So our wing manufacturing, we printed our NACA 4412 ribs just off CAD, and we printed it using ABS filament. We then stuck some carbon rods and just fed them through the ribs so that we had a sturdy wing, and then we mounted them using mounting tape so that they wouldn't move or bend or break. In terms of our wing covers, we decided between tinfoil baking paper and glad wrap. We chose baking paper. It was really flexible. You could stick it down really easily and it was very smooth. Like tinfoil and glad wrap had a lot of dimples in it, break apart easily on impact. So baking paper was just a much easier cover to use.
Our glider construction, so our main focus was our glide polar. So for that we decided an aspect ratio of 10:1 using a dihedral wing. And for this we needed our fuselage to be a bit longer, so we chose 27 centimeters. And we stuck the wings to the fuselage by having a rubber band just strapped around, as you can see in the center. And then we fixed that in place using mounting tape. So if on impact the wings were damaged or bent to a wrong angle, we could just adjust them pretty easily. And we placed our tailplane about 9 centimeters from the back wing. After trial and error, that was the perfect position we found. So in our initial design, we wanted most of the glider 3D printed, such as the fuselage. However, just with trial and error, we found it would be far easier just to have the tailplane and horizontal stabilizer made of balsa wood and have the fuselage just a carbon rod. And just because of the weight displacement this caused, we also had to have a blue tack stopper just at the end, the front of the fuselage.
There were 10 flights performed for the flight test analysis. Of those 10, 5 were selected. The 5 selected were the least affected by wind or bad throws. These flights were individually uploaded onto tracker software that allowed us to track the flight path of each throw and assign XY coordinates to that flight path, and also record the seconds for each position of the glider. The accuracy of this was ensured by calibrating the height of the throw to the thrower's height, and also the length of the throw through by a tape measure was actually glued to the ground. That was about 7.6 meters. These are the flight paths of the selected throws. This is a graph of the flight paths for the 5 different throws. Note that on the x-axis, the flight paths don't go to 0. This is because they often landed out of frame. From this data, we can glean at the glide ratio, which is a measurement of how far the glider travels for every meter dropped in altitude. Note that this can also be calculated from the glide polar plot. And assuming constant speed, the glide ratio can approximate the lift over drag ratio for unpowered aircraft. So we can say the best L/D is 4.9 for our glider. This is the glide polar plot for 5 different throws at 5 different speeds. The gradient of the glide polar line gives us the best glide angle, which is 7.5 degrees. Also note that the sink rate is decreasing, suggesting that the glider performs better at higher speeds. Thank you for listening.